Okay, so now let's have a look at some specific concrete methods. And we start with forward selection feature ranking. So that is a combination of these forward selection methods where we try to start from individual features and add relevant ones. And we look at how to actually evaluate the relevant ones, how to be sure that we add the relevant ones. For that purpose, of course, we need some measures for evaluating individual features, and we will talk about also those specific measures. Yeah. So let's start with that: forward selection and feature ranking. So the general idea is we have as input the target dimensionality k, which should be smaller, of course, than the original numbers of features. Yeah. So we need to give these methods the number of features that we want to extract, actually, that we want to keep. Yeah. So k is the number of dimensions that we want to keep, the numbers of features that we want to keep, and we have a training set of n-dimensional feature vectors, of course, n is the dimensionality, and the target variable. So the training set means that we already have labeled data, so that is a supervised task, actually, or a supervised method in that case. And the general approach of all the detailed approaches is actually that we compute the quality for each dimension, with some specific quality measure. So given a dimension di, compute the quality of di with respect to the target value. So we know the target values, we know the output in the training set, and we try to somehow predict the correlation between the feature and the target variable, the output, the class label, actually. And then we sort the dimensions according to this quality criterion. If the quality criterion means that high values are good and low values are bad, then of course we sort them in descending order, and in the other way, we sort it the other way around, of course. And then we take out of these sorted dimensions, we take the k-best dimensions. So in other words, we look at the individual features, try to quantify the quality of these features, and then take the k-best of these features, actually. And of course, you have to be sure that that relies on an attribute independence assumption, because we look at individual features and then try to take the k-best features. So there are no correlations between features taken into account, because we don't look at combinations of features. We just look at individual features, and the final subspace, the final projection that we output is the set of those k dimensions that we look at. But we don't look at the final output, actually, but we only look, which is a combination of features, we only look at individual features. That's the most important point. The key concept, of course, is how to judge the quality of a feature. So this quality measure is, of course, the key aspect, because everything else is just as some colleagues said, Pipi von der Stange. Sorry for the non-Germans. It's just as simple as whatever. So we just need a quality criterion here. Everything else is just sorting. So what is a good quality criterion? We want to predict. We want to measure how good is the feature for predicting the value of the class attribute, the class label. How good is this feature for predicting the output? And there are a lot of statistical measures typically used for that rely on distributions over the feature values and the target values. That the class variable could be categorical, of course, in terms of classification. Could be also, of course, continuous if it's a regression task. But let's keep the classification task for now. So the question is, how strong is the correlation between these two distributions, the distribution of the feature in question and the output, the class labels? And especially, how good does the splitting the values in the feature space separate the values in the target dimension? And the feature space is just one feature that we currently consider, because we consider each feature individually. So we look at how the feature is actually suitable in order to separate the values in target values, in the target domain, in the class attribute. And that is exactly what we do, for example, in decision trees and stuff like that. So we'll see that most of the methods used in decision trees, of course, are also here good for this task here, of course. Yeah, so how to measure this quality of features, how to measure the distribution of feature values in the given feature and the correlation to the target value. Well, for discrete features or for discrete values, we simply determine probabilities for all value pairs of values. One value of these pairs is the value in the feature, which is evaluated, and the other pair, or the other element of the pair, of course, is a potential output value. Yeah, so we can determine the probabilities for all pairs of values: feature value, output value. For real valued features, we can do both. We can do two different things. These two things here, actually, both of these two things here, orthogonal. So we could discretize the value space, which reduce this case to this case here for discrete values, of course, because if we have discretized value space, then we have discrete values, and we can determine the probabilities again for all value pairs, of course. Yeah? And the second way to do it is to use a probability density function, for example, a uniform distribution or a Gaussian distribution or whatever kind of distribution, in order to model the probability density of, model the distribution of the values of the features. Yeah? And example values or quality measures here are information gain, G-squared statistics, or mutual information. Yeah? And we will have a look at all those three, sorry, in the following here. So first of all, entropy is the basic of information gain. So information gain here relies on entropy, and the idea of entropy is, or information gain is, to evaluate the class discrimination in each dimension, and that measure is actually also used in the famous ID3 algorithm for decision trees. You probably know that there are different algorithms or different measures to build decision trees. One is the so-called ID3 algorithm, which uses information gain, and information gain is based on entropy. So entropy is used to measure the pureness of a data set with respect to some class labels. Yeah, so we still have our class labels, of course, and we have a data set, and the entropy measures the pureness of the data set with respect to the class label. Yeah, so we take a look at PCI, which is the relative frequency of a class CI in the data set S. Yeah, and we just take log2 of this relative frequency times minus the relative frequency, and then sum that up for all the different class labels that we have in our target value. Yeah, and if you know how when you consider the log, well, what is the log? Well, if PCI is 1 for one specific class label, it's 1, then log2 is 0. Yeah, log2 of 1 is 0. If you consider the log, so you have 0 times something gives you 0 for this particular thing. Yeah. On the other hand, if you have 0 in the frequency, then this gives you something minus infinity in that case. Yeah, but minus 0 times log something gives you again 0. Yeah, so in the extreme cases where the frequency of a specific class is 0 or 1. The entropy gives you 0, yeah, and in any other cases it gives you a value above 0. And I mean the catastrophic case, so to say, the worst case is, for example, if you have two classes, yeah, C1 and C2, then in the worst case you have 50% spread. Yeah, so it means that you have 50% observations from C1 and 50% observations from C2, which is something which you cannot use. Yeah, that is the opposite of pureness. Yeah, pureness means the best pureness would be in a 50-50 case. In a two class case would be 0% for the one class and 100% for the other class. Yeah, so and in that case, that is exactly what we said before. In that case, we have 1.0, 100% for the first class, 0% for the second class. In that case, the entropy would be 0. And in the worst case, where we have a 50-50 relationship, yeah, which would be this one here, the entropy would be 1. Yeah? So the entropy is between 0 and 1. The higher it is, the closer to 1 it is, the worse it is. Yeah, the worse it is, and the closer to 0 it is. In the best case, it's 0. The better it is. Yeah. So that is the entropy, which gives you a measurement of pureness of your data set.